Now that we have a pretty solid understanding of our limit machinery, we can come back to the problem that caused us to come up with limits in the first place, which is finding the slope of a tangent line. So let's find the slope of the line tangent to f of x equals x squared at x equals 2. Now that's going to be right here, and you can see the tangent line is going to look something like this. But remember, the problem that we were having with finding a tangent line is that we only know one point on this tangent line. Looks like it's 2, 4. And we decided, so we can't use the usual slope formula because we only have a single point. So what we decided to do was, instead of concentrating on the tangent line, we're going to temporarily come up with a secant line by having another point, which is at some variable x value here, and we're going to slide this x value towards 2. And this sliding process, that's the limit. So what we're going to do is take the limit as x goes to 2 of our slope, which is delta f over delta x. And this should be the slope of the tangent line because so here's our secant line, but as x goes to 2, the secant line sort of turns into the tangent line. So the slope of the secant line should turn into the slope of the tangent line. So all we need to do is calculate this limit. Now, the thing about this slope is that if you try to just plug in 2 right away, you will always get 0 over 0 because, right, if you have two x values that are the same, then delta f is 0 and delta x is 0. So there will always be some sort of algebra or other trickery you need to do on this expression before you actually think about taking the limit. So let's see what we get. Limit as x goes to 2 of, so delta f, that's f of x minus f of 2 over delta x, that's x minus 2. So the limit as x goes to 2 of, let's see, f of x is just x squared minus f of 2, that's 4, over x minus 2. And sure enough, if you just plug in 2, you do get 0 over 0. So we're going to have to, right, 0 over 0 doesn't mean anything. 0 over 0 just means try harder to calculate the limit, try something else. And for this kind of taking the limit of this kind of function, factoring is the usual trick to try. And indeed, the numerator does factor. So this is the limit as x goes to 2 of x minus 2 times x plus 2 all over x minus 2. And now these simplify away. And now we're taking the limit of just a polynomial piece. And we know that polynomials are continuous at all real numbers. So now we can just plug in the 2 and we get 4. Okay, so it looks like the slope of this tangent line is 4. And if you look at the sketch that we have here, that actually looks about right. Right? The tangent line is going about like this, and so it looks like this tangent line is going over 1 and up 4. So this slope, at least on this sketch, this slope seems right. Okay, so in general, the slope of a tangent line at A will be the limit as x goes to A of f of x minus f of A over x minus A. So this is just delta f over delta x. Now, it turns out that frequently writing down the limit this way as x going to A is actually a little bit inconvenient a lot of the time. So we'll use this different variant for how to write down this limit. And here's how that works. So if we have A, right, we have some function, and we have this secant line that goes through A and x over here. Well, rather than letting x go to A, what we're going to do is we're going to name this distance between A and x. We're going to name that h. And that means x is just A plus h. And then rather than x going to A, we're just going to let h go to 0. Because as h goes to 0, this is going to slide that way towards A. You can see it's the same idea, but it just sort of changes where this number is going to. So instead of x going to a, we have h going to 0. Instead of x, right, x is just a plus h, so here's a plus h. And then x minus a, well, x is a plus h. So x minus a is a plus h minus a. The a's cancel, and you just get h. So you can see these two limits are really calculating the same thing. They're just slight variants of each other. And it turns out, sort of experience shows, that the second one is usually the easier way to write down your limit. So with this in mind, let's try a couple examples. So our definitions are over here. Right, here are our formulas for the slopes. So let's find the slope of the tangent line to 1 over x squared at x equals 3. Well, before we do that, let's get a little intuition for what we ought to get. So 1 over x squared looks like this. And 3 is out here somewhere. So the tangent line is going to be like this. So we ought to get a slope that's negative but small, right? A slope that's close to 0 but on the negative side of 0. So with that in mind, let's go ahead and calculate what the tangent slope should be. So our tangent slope, right, we're just going to use one of these two definitions, and I'll use the one with h in it because that's the one that I'm used to. So it's the limit as h goes to 0 of 1 over, 1 over a plus h. So remember a, that's 3. So 3 plus h squared minus f of a, and a is 3, so that's 1 over 3 squared over h. Now, as usual, if you just try to plug in 0, you're going to get 0 over 0. So we have to do some algebra here. Always the goal, right, the limits that come from this slope of a tangent line, the goal is always going to be to cancel this h. If we can cancel that h, right, this is what's causing us to be dividing by 0 when we plug in this 0. So if we can cancel this h, then we can just plug in 0 usually. Okay, so let's see. For this sort of situation, maybe what we should do is multiply the numerator and denominator by the least common denominator of these two fractions. So how about 3 plus h squared times 3 squared? There are other ways to do this algebra, but this will work. So we get the limit as h goes to 0. Now when we distribute this here, in this second factor, the 3 plus h squared cancels and we get 3 squared. And then in this term here, the 3 squared cancels and we get 3 plus h squared. And then in our denominator, we have h times 3 plus h squared times 3 squared. 3 squared is 9. We haven't canceled this h down here yet, so it seems like to have some hope of canceling it, we'd better see what happens to the numerator. Hopefully there will be a factor of h that we can use to simplify. So this is the limit as h goes to 0 of, let's see, 3 squared is 9 minus, and then multiplying all this stuff out, we get 9 plus 6h plus h squared over h times 9 times 3 plus h squared. I could multiply out this 3 plus h squared, but I don't know yet that I need to, so, maybe save that for later. All right, so now continuing to simplify the numerator, it looks like this 9 is positive, that 9 is negative, so these cancel. So we get the limit as h goes to 0. Now everything else in the numerator has a factor of h, so now we can factor out that h, and that's going to leave us with 6 plus h. And then in the denominator, h times 9 times 3 plus h squared. And now we can simplify this h away. All right, so success, right? The whole goal was to cancel this h so that it's safe to just plug in 0 for h, right? After we've canceled this h, the remaining rational function is continuous at 0 because it's defined at 0, so we can just plug in 0. So we get negative 6 over, let's see, we've got a 9 here, and 3 squared, another 9 here. So let's see, cancel a factor of 3, and we get 2 over 27. Okay. All right, well, you can see that we were expecting a slope that is negative but pretty small, and sure enough, that's what we got. So this seems plausible, at least. To get a really firm geometric idea of if this looks right, we would have to get an accurate graph, maybe using GeoGebra or something like that. But I believe it. I think we did it right. Okay, let's look at one more example. Let's find the equation for the tangent line to g of x equals square root x at x equals 1/2. So the square root of x looks like this. Right, this is y equals square root of x. And let's see, 1 is about here. And so 1/2, it's going to be about there. Okay, we can find, so there's a tangent line that goes through this point, and we can find what this point of tangency is just by plugging in 1/2, right? So this point is 1/2 comma g of 1/2, but g is the square root function, so this is 1/2 comma 1 over root 2. So we have a point on this line, but we don't know the slope of this line, right? If we know a point and the slope, then we can write the equation of the tangent line. So we just need to find the slope of this line. But it's a tangent line, so let's find the tangent slope. So that's going to be, right, m sub t. So this is the limit as h goes to 0. As we're writing this out, remember that this x value, this is playing the role of a. So limit of f of, sorry, not f, g of 1/2 plus h minus g of 1/2 over h. Okay, so limit as h goes to 0. As usual, if we tried to just plug in h equals 0, we'd get 0 over 0. We need to somehow cancel that h down there. So g of 1/2 plus h, that's the square root of 1/2 plus h, minus g of 1/2, that's the square root of 1/2, and then the denominator is just h. All right, so we need to do some kind of algebra so that we can cancel this denominator. What sort of algebra tricks do we have available when we have square roots floating around? Well, we can rationalize. Right? We can multiply the numerator and denominator by the conjugate of the stuff in the numerator. So that's going to be square root of 1/2 plus h. And then instead of a minus, it's a plus square root of 1/2. And then in the denominator as well, square root of 1/2 plus h plus square root of 1/2. So this is the limit as h goes to 0. Now in the numerator, when we multiply this all out, remember the cross terms cancel. That's the whole point of multiplying by the conjugate here. So we get first times first is 1/2 plus h, and then minus second times second is 1/2. And then these terms, when I say the cross terms cancel, I mean this term times that term is the negative of this times this, so those cancel. Now in the denominator, we get h times this big mess, square root of 1/2 plus h plus square root of 1/2. All right. Now in the numerator, we have a plus 1/2 and minus 1/2, so those cancel. And now the only thing left in the numerator is h. And so finally, we can cancel the h. Remember, when you're canceling something in the numerator and denominator, when you're canceling a common factor in the numerator and denominator of a fraction, it's 1 that's left over when you cancel everything. So what we're left with is the limit as h goes to 0 of 1 over square root 1/2 plus h plus square root 1/2. And now, as usual, once we've canceled that h, usually the remaining function that you're taking a limit of is continuous at 0, and this one is no exception, right? We know that roots are continuous, sums are continuous, quotients are continuous, as long as the denominator isn't 0, so it's safe to just plug in 0 here. And we get 1 over, looks like it's going to be 2 times the square root of a half. Okay, or another way to write this is, let's see, 1 over 2 over root 2. So yet another way is root 2 over 2. Maybe we'll stick with that way of writing it. All right, so this is the slope of our tangent line. We already had a point on our tangent line, so now we can write the equation of the tangent line. So the equation of the tangent line at x equals a half is, we can use the point slope equation for a line. So y minus the y coordinate equals our slope, root 2 over 2, times x minus the x coordinate. Okay. And then if we wanted to, we could put this into slope-intercept form. I don't know that that's really necessary, but it's possible. We can do it if we want. So this is y minus 1 over root 2 is the square root of 2 over 2 times x minus, looks like root 2 over 4. Then add 1 over root 2 to both sides. So y is the square root of 2 over 2 times x minus root 2 over 4 plus 1 over root 2. If you rationalize 1 over root 2, that's actually the same thing as root 2 over 2. So this is y equals root 2 over 2 times x, and then minus root 2 over 4 plus root 2 over 2. That's plus root 2 over 4. So there's the equation of our tangent line. Of course, you know, finding the point for this equation was the easy part. It's finding the slope for this tangent line that's the tricky part, because we have to calculate this limit.